Let's take a quick look at the learning targets for our fourth week of distance learning, April 20 through 24th, for Algebra 2. So I apologize for the sloppy writing here, but our targets are about expected value. That's kind of a target on its own. And then the following three things can kind of be grouped together because they're all the similar style of question, but you have the permutation, combination, versus fundamental principle of counting. So expected value is the average outcome if you were to play the game many times. And so expected value is typically used when you're getting a score or getting points or getting a cash value. So it's essentially if you were to play this game a whole bunch of times and you add up all your different winnings of different types and then you averaged it, that's what the expected value would be. A permutation is when you have a set of R things from a group of n items. So n is the total sample space or the group of things, r is how many you're choosing, and permutation is when order matters. So a couple examples, like if you have different titles, meaning like president, vice president, secretary, places in a race, first, second, third, or orders on a shelf, like if you're looking at a shelf, the order would matter. And then you use your calculator and use the NPR option, which is in the video for that lesson to find out that quantity, a number of ways that can occur. And then we have combination, which is very, very similar, but instead the order does not matter. Right? So you're doing the same thing. You have R items from a group of a total of n, but the order doesn't matter. So you're on the team, you're a member of the team, doesn't matter which one. You're mixing things together, or you have subgroups. Finally, you have fundamental principle of counting, which is then when you have an item from different groups. So you select an item from multiple different groups. It's like a Subway sandwich. You can choose a crust, a meat, a cheese, and veggies. Or an outfit, you have one t-shirt, one sweatshirt, one pair of sweatpants, etc. And then you just multiply all those things. So that's an example of expected value. So remember, it's the average outcome if you play many times. In order to calculate that average outcome, you find the probability of one particular outcome and you multiply by it. And then you add the next one, and the next one, and the next one. You keep on going. I think a table is a great way to organize all of your information for this. You have what the outcomes are, you have the probabilities of those specific outcomes, and then you multiply them. Also, a very common question having to do with expected value is if it's at a fair game. And it's a fair game if and only if the cost to play is equal to the expected value. This is a very simple question, and one that students get wrong often. It's not whether it's more fair to you or fair to somebody else. It's only a fair game if the cost to play is equal to the expected value. So we're going to look at an example here. It looks a little complicated, but it's not too bad. It has to do with the deck of cards because some students struggle with those concepts. So that's why I chose that example. So you pay $4 to play and you pick a card, a single card from a deck. If it is black, you win $2 back. If it is a heart, you win $3 back. If it's a diamond face card, you win $4. But if it's the ace of diamonds, you win $110. Right? So that's a pretty good win if you only paid $4 to play. So let's take a look at what that expected value would be. So what we're going to start with is we list what the outcomes are. And so the outcomes are not a black card. The outcomes are like what the value is. So if the card is black, you win $2. And so that's a $2 win. And then a black card, so that would be either clubs or spades. So that's half the deck. So half the deck, you can win $2. If it's a heart, you're going to win $3. So I go, okay, so now I'm winning $3, and a heart is a quarter of the deck. So right there, we have 3/4 of the way to win something. Then we have, if it's a diamond face card, you win $4. So we're going to win $4 here. Now face cards, Jack, Queen, and King, but it's only the diamonds. So you have 3 options out of all of your 52. And then finally, we have if it's the ace of diamonds, you win 110. So we have 4 different ways to win, the last one being winning 110, but there's only one way you can win that. And now what we do is we just multiply all of these values times their respective probabilities. So if we do that, I like to just use the fractions. So this is just 1 because 2 times 1/2. This is 3/4. This is going to be 12 50-seconds because 4 times 3. And this is going to be 110 50-seconds. And so I just multiplied those different probabilities by their values. And now what you do is you just add up all of those things. So all 4 of those, you add them up and figure out the value. And if you use your calculator to do that, what you end up with is $4.09 or 9.6 cents. We're going to round that up to $4.10. So that is our expected value. What that means is if we were to play this game many, many times and add up all of our different winnings and then divide by how many times that is, it would be $4.10. Expected value is not what you expect to happen, because if I expect to happen, what's most likely is that I pick a black card. But that's not what expected value is. It is the average outcome. And so if you play this a bunch of times, you add up. Sometimes you get 2s, sometimes you get a 3, maybe once you get 110. Average them out, you're going to get 410. Now, is that a fair game? You might be saying, well, wait a minute, I win $4.10, but I paid 4? Heck yeah, I'm taking that. Well, that's not the question. The question isn't whether you should play it, but whether it's a fair game. And no, it is not, because those things are not equal to each other. Let's move on and talk about permutation, combination, and fundamental principle of counting. These are all very similar style of questions, but as you can see here, we have what's the difference between a single sample space and multiple sample spaces. And we haven't talked a whole bunch about sample spaces in our Algebra 2 work, but it's just essentially it's a set of things or values that you're going to be able to pull from. And so a permutation versus combination, those both come from a single sample space, whereas multiple sample spaces is a fundamental principle of counting, right? And when we take a look at these examples, so I have 3 different examples, 1 of each. So let's say we have 7 Twins jerseys. It says, how many ways can you pack 3 in a suitcase? Versus question 2, you have those 7 Twins jerseys, but how many ways can you wear them on Friday, Saturday, Sunday? And so you can see the difference in that phrasing there between these 2 questions is that when I pack 3 in a suitcase, that doesn't imply that the order in which I pack them really matters. Versus if I'm wearing them on Friday, Saturday, Sunday, yeah, the order would matter. And so that's the difference between order mattering versus not. They both come from a single sample space. My sample space is the Twins jerseys, and there are 7 of them in this particular scenario. And so for this question, you're just going to do what's 7C3. That's the notation we use. So you have 7 things, you're choosing 3 of them, and if you do that on your calculator, and the video for the lesson talks about that, you should get 35. So there are 35 different ways you can pick 3 or pack 3 in a suitcase. Versus the permutation looks very similar, but it's 7P3, and on your calculator you do that same work, where in this scenario now you have 210 ways. You have 210 ways, and almost always, if something is a permutation, you're going to have more ways to do it. That's because the order in which you do it does matter. Right? So versus order not mattering, order does matter. Now this last question, I have those same 7 Twins jerseys, but now I also have 3 Twins hats, some shorts, and some sandals that I'm going to wear to the Twins game. And it says, how many different outfits can you wear? Well, I'm not picking 3 out of my Twins jerseys or anything like that. I'm picking 1 Twins jersey, and so sometimes we use like these decision blanks here. So we have jersey decision, so how many options do I have? And then you multiply by your hats, and then you multiply by your shorts, and you multiply by your sandals, right? So it's essentially saying how many ways can you choose to fill in those blanks. So I have 7 options for my jerseys, I have 3 hats, I have 5 shorts, and you have 4 sandals. So when you do that, then you just get to multiply all those things, and that's what the fundamental principle of counting is talking about, where you're going to have 420 ways that you can make an outfit with that particular wardrobe. Right, so decision blanks are how many options you have for those things, and that's a fundamental principle of counting when you have different sample spaces, jerseys, hats, shorts, versus permutation combination. You have just 1 sample space. You have to figure out if the order matters or order does not matter. Hopefully that helps, and good luck this week.